Okay, so here's the second part to the 5.2 lesson where we look at actually how to expand binomials using combinations. Instead of having to write out Pascal's triangle to figure out the coefficients of the terms in the expansion, I'm now going to teach you how to just use combinations to determine the coefficients. So back in grade 11, what you would have done, you probably would have expanded out a bunch of binomials, and it would have taken a long time, but these are the answers you would have gotten. Well, first of all, a plus b, okay, there's a binomial. It has an exponent of 0. Anything to the exponent of 0 is 1. No problem. A plus b to the 1 is just a plus b. A plus b to the 2, well, that's where you would have had to remember FOIL. A plus b squared means a plus b times a plus b. And you would have done FOIL. A squared plus ab plus ba plus b squared. And that would have given you a squared plus 2ab plus b squared. Next, you would have done a plus b to the 3. You would have added another factor. When you do that, each of the term, okay, so when you did a plus b times a plus b, each of the term in the first binomial had to be multiplied by each term in the second binomial. Now each term in the first binomial is going to be multiplied by each term in the next two binomials. So we're going to get, it's going to get increasingly more complicated, but this is the answer you would have got. You would have been able to do it. It might have taken a little bit of time. A plus b to the 4, there would have been another factor of a to the b that has to be expanded into as well, and it keeps getting increasingly complicated. But after you would have expanded those out, what you probably would have done is filled out what's called Pascal's triangle, where you write down the coefficients of each of the terms in the expansion. So if we were to fill that out, when the exponent on the binomial is 0, the coefficient, well, the only term we have is a constant term, 1. For the binomial with an exponent of 1, the coefficients were 1 and 1 on our terms. For the expansion of a plus b to the 2, so the exponent is 2, the coefficients were 1, 2, and 1. 1, 2, and 1. When the exponent was 3, a plus b to the 3, so a binomial with an exponent of 3, the coefficients were 1, 3, 3, and 1. 1, 3, 3, and 1. And when the exponent was 4, it was 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. When it was 5, it was 1, 5, 10, 10. 1, 5, 10, 10, 5, 1. So keep in mind, we're looking at the coefficient of each of the terms in the expansion. 1, 5, 10, 10, 5, 1. And at that point, you would have noticed a pattern. Hopefully, you've noticed a few patterns. First of all down the left side are all 1s. All down the right side are all 1s. And to get the terms in between, all you have to do, so to get this term, I just have to add the two terms directly above. 1 plus 5 is 6. 5 plus 10, 15. 10 plus 10 is 20. 10 plus 5 is 15. 5 plus 1 is 6. And so on for the bottom row. 7, 21, 35, 35, 21, 7. Okay, so that's Pascal's triangle. So if we were to expand a binomial with an exponent of 7, these would be the coefficients of the terms, and there would be 1, 2, 3, 4, 5, 6, 7, 8 terms. Notice if the exponent was 6, there would be 7 terms. If the exponent was 5, and on a binomial, we expanded the binomial, there would be 6 terms. So there's always one more term than whatever the exponent is in the expansion. There's a few other patterns in Pascal's triangle, but that's probably the main one you would have discussed back in grade 11 math. Okay, so here's just some more of the patterns. So it's symmetrical down the middle, another nice thing to notice, symmetrical down the middle. Each row is a power of 2. If you were to add up the coefficients, it would equal a power of 2. The outside number is always 1. And we talked about this. Number inside row is the sum of the two numbers directly above it. Like, look, 2 plus 1 gives us 3. Where did this 10 come from? 4 plus 6. Okay, that's just a nice pattern in Pascal's triangle. And there's lots of other patterns as well. But this is just a quick review of what you would have done in grade 11. Okay, so this is how it's going to change now. You are no longer going to have to write out Pascal's triangle when expanding a binomial to figure out the coefficients. I'm going to show you a new way. So let's think about it. We're going to focus on a plus b to the 4. So we're going to focus on this expansion right here. Just looking at that expansion, okay? And more specifically, we're going to look at this term in the expansion of a plus b to the 4. One important thing I want you to notice, actually before we move on, is if you look at the exponents on each term. So in this expansion, look at the exponents. On the first term, we have an a to the 4, and I guess there's a b to the 0 as well there, okay? But because it's b to the 0, b to the 0 is equal to 1, so we don't need to include it. So, but look, the sum of the exponents, 4 plus 0, is 4. That adds up to the exponent on our binomial. Here, we have a 3 and a 1. 3 plus 1 is 4. Here we have a 2 and a 2. 2 plus 2 is 4. Here we have a 1 and a 3. 1 plus 3 is 4. Here we have a 4 and a 0. 4 plus 0 is 4. They all add to whatever the exponent on our original binomial was. And the one below, look, we have an a to the 4. Oh, just lost. Let's see if it pops back up if I open it up. Reopen. Hopefully it reopens for us so I don't have to start the video again. Yes. Come on. Part 2. Good. I don't think that's the one I want. Yeah, this is the one we were just working on. Okay, let's just continue with this. Okay, so I just highlighted this, and I was just showing you how the exponents on each term in the expansion equal the sum of the exponents in each term in the expansion equal the exponent on the original binomial. Like here, 4 plus 1 is 5. Here, 1 plus 1 is 2. Okay, that's important to notice. So, and like I said, we're now going to use combinations to figure out coefficients instead of using Pascal's triangle. So, the coefficients in the expansions can be determined using a strategy very similar to the one we used when analyzing pathways through a map grid. That's why those two types of problems are in the same lesson. So let's look at the term that includes a to the 3, b to the 1 in the expansion of a plus b to the 4. And remember, notice the exponents add together to give you the exponent on the binomial. But let's look at that term in our expansion. So this one right here. Notice that term has a coefficient of 4. Let's take a look and try and understand why does that have a coefficient of 4. Other than the fact that the 2 in the row above, the coefficients of the 2 in the row above add to 4, well, why is it a 4? Okay, let's start to think about it. So it's the result. So a cubed b, what does that really mean? That means a, whoops, I don't want to do this in highlighter. A to the power of 3 times b, that really means a times a times a times b. That's what that means. That equals a to the 3b. Or it could be, it could be a times b times a times a. That also equals a cubed to the b. Maybe if we figured out how many ways we could rearrange these letters, that would tell us the coefficient for that term. And that's in fact what we're going to look at. So if we consider that term, a cubed to b, it's the result of multiplying 3 factors of a with 1 factor of b. Okay? 3a's, 1b. That equals a cubed to b. There are 4 ways that can be done. These are the 4 ways right here. Oops, I only circled 3 of them, but you can see the 4. It could be a times a times a times b, or a times a times b times a, or a times b times a times a, or b times a times a times a. Well, we don't have to write out all of those all the time to try and figure out the number of ways it could happen, so we're going to think of it as a combination. So keep in mind, when you're expanding a plus b to the 4, that means you have 4 factors of a plus b all being multiplied together. So each term in this first binomial has to be multiplied by each term in the remaining 3. So when I get a cubed b, what has happened is you've multiplied 3 factors of a together and 1 factor of b. So you could have done a times times b. That would give you 3a's and 1b. That would give you a cubed b. Or what could have happened was it could have been in a different order. It could have been a times b times a times a. So all of these different orders have to happen in the expansion because each term in each binomial has to be multiplied by all the other terms in the other binomials. So you would have gotten all of these 4 different arrangements. But basically what's happening is for a cubed b, there are 3 factors of a, 1 factor of b. How many ways could that have happened? How many ways could we choose one of the 4 factors to be a b? Do 4 choose 1? And if you evaluate 4 choose 1 using the combinations formula, you get 4. Or you could think of it as how many ways could we choose 3 of the 4 to be A. 4 choose 3 also gives you 4. Okay, so if we look back at our expansion, if we look at this here, 10 a squared b cubed, why is the coefficient 10 on this term? Well, there are 2 factors of a, 3 factors of b, so there are 5 factors. How many ways could we have chosen 2 of those 5 factors to be an a? Well, if we do 5 choose 2, let me just turn this on here. If we do 5 choose 2, we get 10. Or 5 choose 3 also equals 10. If we want to figure out how many ways could 3 of the 5 spots be b, that's why the coefficient is 10. Okay? So, I've just recorded that here. So there are 4 available. So if we're once again talking about this a cubed b in the expansion of a plus b to the 4. There are 4 available spaces to record a's and b's. For the term a cubed b, 1 space has to be occupied by a b. Therefore, there are 4 choose 1 ways of doing this. Or 4 choose 3 is equivalent. If we want to think of choosing spots for a's instead of choosing spots for b's. Therefore, the coefficients of the general binomial expansion a plus b at the end can be represented by Pascal's triangle in terms of the combinations formula. So we could fill out Pascal's triangle using combinations. Okay, I'm not going to explain this too much because I don't want to overcomplicate it, but basically to get the coefficients, so let's look at the 4th row here, the 4th row. What we have, notice we're all using combinations in the form n choose r, where n is the exponent on the binomial. That's why the n value for each of the combinations are 4. And then for each term in the expansion, the r value in the combination is the number of spots that need to be occupied by a b. So if we look back to our expansion of a plus b to the 4, in the first term, no spots need to be multiplied by a b. Then 1 spot, then 2, then 3, and then 4. So notice it increases by 1 each time until we get to n choose n. So 4 choose 4. For this one, it would be 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, 5 choose 5. Okay. So that's where this Pascal's triangle comes from, using combinations formula. These combinations will give you the coefficients on your terms in the expansion. So here, this formula looks fairly complicated. What I want you to focus on is mainly this will give you the general term in the expansion of each binomial. Okay, so look at the pattern from our triangle, and you notice each combination has an n value of whatever the exponent on our binomial is, and then the r values start at 0 and increase until you get to n choose n. So if we had an exponent of 3, it would start with 3 choose 0, then 3 choose 1, all the way up to 3 choose 3. To get the exponent on your a and your b in your term, okay, the a value is going to start off with n and then decrease by 1 each time, and then the b value is going to start at 0 and increase by 1 each time. And if we look back at our expansion, that's the pattern. So if you look, the a value started off by 4, then went 3, 2, 1, 0. And the b value started at 0 and went up to 1, 2, 3, 4. Okay, so let's practice expanding a binomial. Once you see the pattern at work, it's not too difficult. But the main formula we want to remember, this gets us the general term. So the general term, we do n choose r, a, whoops, I want to get this, oh, sorry, move this out of the way. I want to get a to the n minus r, b to the r, and that'll give us the general term in our expansion. So keep in mind, I'm just going to label this here. So the exponent on the binomial is always your n. Whatever term is here is your a, and in this case, we've just kept it simple and used an a, and whatever is here is your b. And your r value represents the number of spots needing to be, number of factors that are going to be b's in the term. And it's always going to start at 0 and keep increasing until you get to an r value that is equivalent to the n value. So it's going to start with n choose r. So it's going to start with 6, choose 0. And then a to n minus r, so to 6 minus 0, which is 6. B to the r. In this case, r is 0. And then that's your first term, plus your second term. Since our first one was 6, choose 0, the next one is 6, choose 1. A to the n minus r, so a to the 6 minus 1, which is 5. B to the r, which is 1. 6, choose 2. A to the n minus r, so 6 minus 2 is 4. B to the r, which is 2. Hopefully you're noticing the pattern. The a's are decreasing by 1, and the exponent of the b's are increasing by 1. So 6, choose 3. A to the n minus r, so 6 minus 3 is 3. B to the r is 3. Plus 6, choose 4. A to the n minus r, 6 minus 4 is 2. B to the r, which is 4. Plus 6, choose 5. A to the 6 minus 5, which is 1. B to the r, which is 5. Plus 6, choose 6, and this is going to be my last term because my n and my r values have now reached the same value. A to the 6 minus 6, which is 0. B to the r, which my r value is 6. So there we go. Now I just have to simplify all of this. So for my first term, 6 choose 0 is equal to 1. So I have 1 a to the 6. Because b to the 0 means the b is gone, because b to the 0 equals 1. My next term, 6 choose 1 is 6. A to the 5, b to the 1. I can't simplify that at all. My next term, I'm going to have to do 6 choose 2, and I get 15. Plus 6 choose 2 is 15. A to the 4, b to the 2. My next term, 6 choose 3, will give me 20. 6 choose 3, 120, sorry. 120. A to the 3, b to the 3, plus, 6 choose 4 is going to be the same answer as 6 choose 2. It'll give me 15. A to the 2, b to the 4, plus 6 choose 5, it's going to be the same as 6 choose 1, which is 6. A to the 1, b to the 5, plus 6 choose 6, which is equal to 1. A to the 0 is 1, so the a is gone. B to the 6. There's my answer in the expansion of a plus b to the 6. Now let's do an example where we're going to change the letters a and b to actually have numerical values or have a variable in there that's not a or b, so we can learn to substitute into our formula. So here's an example. 2x minus 3 to the power of 5. So we have a binomial that needs to be expanded. Here's our a value. Here's our b value. And remember, the exponent on the binomial is your n value. And we're going to keep using our general formula, n choose r, a to the n minus r, b to the r. And we're going to use that for every term in our expansion. And remember, there's always going to be 6 terms in our expansion here. Because the first term is going to be 5 choose 0 as the coefficient, then 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, until we get to 5 choose 5, and that'll be our last term. The number of terms is always one more than the exponent. So our first term is going to start off with 5 choose 0. And then our a value is 2x, so it needs to be 2x to the n minus r. So 5 minus 0 is 5. Make sure you put the 2x in brackets so you know the 5 has to be applied to the 2 and the x. And then our b term is negative 3. Don't forget that negative has to stay with that 3. To the exponent of r, and our r value is 0. There's our first term, plus the next term. 5 choose 1. And then our a value is 2x to the exponent of n minus r. 5 minus 1 is 4. And our b value has an exponent of r on it. So my r value is 1, exponent of 1. And 5 choose 2, and hopefully you're getting the pattern. The exponent on the a values is going to keep decreasing by 1. So this will be a 3, because 5 minus 2 is 3. And the exponent on the b value is going to keep increasing by 1. 0, 1, this one will be a 2, because the r value is 2. Plus 5 choose 3, 2x to the 2, negative 3 to the 3. plus, I have two terms left, 5 choose 4, 2x to the 1, negative 3 to the 4, plus 5 choose 5, that's my last term. Once the n and the r value have the same value, that's your last term. 2x to the 0, 5 minus 5 is 0, negative 3 to the 5. Now let's look at how we could simplify this. Okay, so let's look at just the first term. 5 choose 0 is 1. So this equals 5 choose 0 is 1. Now I have to do, keep in mind this exponent of 5 has to be applied to the 2 and the x. So I have to figure out, okay, what's 2 to the 5? So 2 to the exponent of 5, and you get 32. So here, this 1 is going to have to be multiplied by 32. And then there's an x to the 5 after that, and then negative 3 to the 0 is just 1. And I could then simplify this, doing 1 times 32 times 1 is just 32. So my first term is just going to be 32 x to the 5. Oh, this is lagging on me. 32 x to the 5 is the first term in the expansion. The next term, I'm going to have 5 choose 1 is 5. I'm going to have to apply this exponent of 2, or the exponent of 4 to the 2 and to the x. So 2 to the 4 will give me 16. So I have 16 and then x to the 4. And negative 3 to the 1 is negative 3. So how could I simplify this term? I could do 5 times 16 times negative 3. And that would give me an answer of negative 240 x to the 4. That's how I could simplify that. And then the next term, I would do 5 choose 2. So 5 choose 2, and that'll give me a value of 10. I don't have to apply this exponent of 3 to the 2 and the x. So 2 cubed is 8. X to the 3, and then negative 3 squared is positive 9. Negative 3 times negative 3 is positive 9. 10 times 8 times 9 would give me 720 x cubed. And then the similar principle for the rest of them. I'm not going to go through all of it. These would be the last three terms in the expansion as well. Okay, so let me just erase this so it looks a little less confusing since I didn't finish that one off. And this would be your final answer in the expansion. Okay. And like I said, we went over the first three terms. Follow the same principle to get the last three terms by simplifying these last three terms in our expansion. Okay. Next thing you're going to have to do is you're going to have to be able to find, instead of expanding an entire binomial, I'm going to ask you to be able to find specific terms in the expansion, maybe even finding a constant term in expansion, and I'll explain what that is in a second. So to find a general term in the expansion of a plus b to the n, we've talked about this already. You do n choose r, a to the n minus r, b to the r. What I haven't really talked about yet is this, to get term r plus 1. If we look back at our expansion, to get the first term, the r value is 0. To get the second term, the r value is 1. To get the third term, the r value is 2. The r value is always 1 less than whatever term you're trying to find. That's why, to find term r plus 1, we do this. So we want to find the first term, we plug in 0 for r in all the spots. If we want to find the third term, we plug in 2 for r in all the spots. Okay? So, what is the fifth term in the following binomial? Using this form, if we want the fifth term, remember the r value is always 1 less than the term number. So I want the fifth term, I need to plug in 4 for r. So term 4 plus 1, that equals 5, so that's term 5, equals, here's my n, here's my a, here's my b. So if I want term 4 plus 1, that's term 5, that's what I'm looking for, the fifth term. I need to do n choose r. So 6 choose 4, I plugged in 4 for r. R is always 1 less than the term number. My a value is x squared, so I have to do x squared to the n minus r, so to the 6 minus 2, which is 2. And then my b value, which is negative 2, to the exponent of r, which is 4. Now I just have to simplify this. I have to evaluate 6 choose 4. Oops. 6. 6 choose 4 is 15. X to the 2, power by power, multiply the exponents. 2 times 2 is 4, x to the 4. And then negative 2 to the 4. So negative 2 times negative 2 times negative 2 times negative 2 will give me 16. So how could I simplify this? What we have to do, we just have to do 15 times 16. Give me 240 x to the 4. That would be, if we were to expand out this binomial, this would be the fifth term. There would be 7 terms in the expansion, but this would be the fifth term in the expansion, 240 x to the 4. How about if I wanted to find the third term in the expansion of this? This is the first time we're going to have a fraction as our b value. And I'll show you how that works. You just have to remember your exponent laws. Okay, what if I wanted the third term in this binomial expansion? So remember, if you want the third term, the r value is always going to be 1 less than the term number. So if I want the third term, this r value would have to be 2 to get term 2 plus 1, which is 3. So to get term 2 plus 1, which is 3, the third term, what I have to do, first of all, remember, here's your a, here's your b, here's your n. I have to do n choose r, so 8 choose 2. I plugged in 2 for r. My a value is x. To the n minus r, which is 8 minus 2, which is 6. To the b, which is 1 over x, to the r, which is 2. Now I just have to simplify this by figuring out what 8 choose 2 is. 28. X to the 6. And then keep in mind this exponent of 2 is applied to the numerator and the denominator. So that's equal to 1 squared over x squared. Well, 1 squared is just 1, so it's equal to 1 over x squared. Now, a couple ways to think of this. Well, 28 times 1 is 28, so that's fine. You could remember the quotient rule when you have two powers being divided with the same base. So I have x to the 6 divided by x squared. You just have to subtract the exponents, so that'll equal x to the 4. Or what you can do, you can bring that x squared to the top of this fraction by changing the sign on the exponent. So it would become x to the negative 2. And now you have two powers being multiplied together that have the same base. X to the 6 times x to the negative 2. When multiplying powers of the same base, you just add the exponents. 6 plus negative 2 is 4. So 28 x to the 4 would be the third term in the expansion of this binomial. Let's work on finding, we're going to work on finding a constant term, okay? So if I want to find a constant term, so finding constant terms, what we're first going to have to do, we're first going to have to find the general term in the expansion by filling in everything that we know. We'll know the n, the a, and the b, but what we're going to have to do, so first of all, a constant term means a term with no variables. So we're going to have to figure out, is there any way we could plug in a value for r that would make the variable disappear? Is there any way we could plug in a value for r which would make the exponent on the variable be 0? That's the only way we can make the variable disappear. So let's figure that out. Determine the constant term in the following binomial. So here's my binomial, a, b, n. So I could expand it all. There would be 11 terms in the expansion and see if any of them are a constant term, meaning that there's no variable associated with it. But that would take a long time. So what we're going to do is we're going to write out the general term by plugging in our a, b, and n into our general term formula. So remember, it's term r plus 1 equals n choose r. Well, n is 10. I know that, but I don't know which term is going to be the constant term, so I can't plug in for r yet. I do know the a value, that's x, and that'll be to the 10 minus r. And I do know the b value, which is 1 over x, and that'll be to the exponent r. Now let's simplify if we can. So 10 choose r, I can't simplify that. X to the 10 minus r, I can't simplify that. But here, I have 1 to the r over x to the r. Well, 1 to the r is just going to be 1, because 1 to the exponent of anything is 1. So I can ignore that. And this exponent of r is also going to be put onto that x. So this is equal to 1 to the r, which is 1, over x to the r. What I'm going to do now, I'm going to take this x to the r, bring it to the top of the fraction by changing the sign on the exponent. So that'll just become 1 times x to the negative r, which is just x to the negative r. Now I have two powers being multiplied together that have the same base, just add the exponents. So 10 choose r, x to the, and then add these exponents together, 10 minus r plus negative r. That'll give me 10 minus 2r. Okay, now I have to think, is there any value for r? So I'm going to make a note here. Constant term. To get the constant term, I'll write exponent on variable has to equal 0. A constant term means there's no variable, it's just a number. So to get that, I would have to figure, is there any way I could plug in a value for r which would make the exponent on this x be a 0? So let's just solve that. So what value could I plug in for r to make 10 minus 2r equal 0? 10 minus 2r equal to 0. Solve that. 10 equals 2r. That would mean 5 equals r. So if r was 5, the exponent on the x would be 0, which would eliminate the x, which would mean we have a constant term. So all I have to do now is take this value for r and plug it in to my general term that I've now figured out. So let's do that. So I have 10 choose 5, x to the 10 minus 2 times 5. So I have 10 choose 5 to the x to the 10 minus 10, which is 0. So what's 10 choose 5? 10 choose 5 is 252. So I get 252. X to the 0 is equal to 1, so 252 times 1, which is just 252. That would be the general term in the expansion of this binomial. So if I expanded out that entire binomial, the sixth term, since my r value is 5, it would be the sixth term. The sixth term would have been 252, and there would be no variable associated with it. Okay, so that's it for this lesson. For this section, you definitely have to practice expanding the binomials. So make sure you get the worksheet from jensenmath.ca. Try it out. Just let me know if you have any questions.